Hello everyone, thank you for attending my session. My name is Yilun Wang from Xianyang University. I'm presenting my work, InferLog, accelerating LLM inference for online log parsing via ICL-oriented prefix catching. In recent years, large language models have changed log parsing, achieving total accuracy thanks to their semantic and understanding and feature learning capability. However, there is a critical gap between this log parser and actual deployment in modern software systems. In online environments, commercial API pose privacy risks, and local deployment facing stringent requirements on latency and throughput. Therefore, our goal is to develop an efficient local LLM inference system to handle massive log parsing requests and meet service level objectives. To achieve this, we first look at the mechanism of LLM inference. There is a key mechanism called prefix catching. It can avoid recomputing key value hidden states for identical prompt prefix. For example, for single request, it can avoid calculating the key of all inputs when generating the next token via auto-regression. It also benefits for cross requests that share the same prefix token. Meanwhile, in context learning, ICL is widely used to improve log parsing accuracy. For log parsing requests, it adopts prompt format like this: common instruction, demonstration examples, and queried logs. From the terms of key catch reusing, the default prefix catching setting, only common instruction can skip key catch computing, but InferLog finds the opportunity for the ICL parts, which consumes the majority of the prompt tokens. We also introduce LLM inference system parameters. They determine how the inference system schedules and process requests. A good parameter setting can improve the throughput, obviously. Our first motivation stems from the performance bottlenecks we observed. When simulating online log parsing scenario with massive concurrent invocations, we found it challenging to inference performance. Through the detailed latency attributions, it becomes clear that the primary performance bottleneck occurs during the prefill stage rather than the decoding stage. Why is prefill stage so slow? Because in traditional prefix catching, it cannot effectively reuse the key catch for the ICL part. In existing system, dynamic example selection and specific permutation disrupts the prefix structure. In our study, the average prefix catch hit rate was only around 50% for the ICL part. However, we noticed an opportunity to refine the ICL examples. It could significantly benefit from prefix catching. Our third motivation involves the system configuration itself. We found that the default inference parameters often underperform for specific workloads. While appropriate parameter settings are crucial for ensuring service level objectives, existing tuning methods are highly time-consuming. They cannot effectively suggest configurations for online inference workload in a timely manner, as we have a very limited tuning budget for finding optimal configurations. To address these challenges, we propose InferLog. InferLog is designed for LLM-based log parsing system with two core modules: ICL-oriented key catch reusing and fast inference config tuning. Let's dive into the first module. We introduce a prefix-aware ICL refinement mechanism. Instead of randomly reorganizing ICL demonstration, we maintain an ICL table using a variant of the list recent use strategy to track demonstration set that already have the key catch in inference system from history requests. When a new request arrives, we execute 3 steps. First, matching. We find the target demonstration set in the ICL table that shares the longest common prefix with the current request. Second, modifying. We update the the examples to align with the target set when current example and the target example share the same log templates. Third, reordering. We align with the order of the target LCL example to maximize the KV catch hit rates. For our second module, we formulate configuration tuning as an optimization problem to minimize latency and improve throughput. We chose meta-learning as the key framework to learn the relationship between configurations and inference performance metrics. Our basic algorithm, MAML, that provide good weighted initialization of a model from offline training and can achieve strong generalization to adapt to new tasks after a few gradient descent steps. However, standard meta-learning like MAML treats the average gradient from different source tags as the learning signals. It fails to discern the relative importance of different tasks. Therefore, we design attention MAML, which introduces an attention mechanism and a weighted meta-loss to automatically learn the weight from different source tags. We then integrate attention MAML as a surrogate model into a SMBO framework by utilizing Monte Carlo dropout for uncertainty approximation and employing a warm start strategy. We can rapidly discover optimal LLM inference configuration under strict time constraints. We then introduce our experiments. We evaluate the InferLog using LogHub 2K dataset, and we integrate our InferLog into VLM inference system. We use Queen 2.5 40 billion for the log parsing on NVIDIA Tesla A40 GPUs, and we compare InferLog against several inference acceleration baselines, including VLM default, traditional prefix catching with truncate fill, and bench LLM. Compared to the baseline inference accelerating method, InferLog significantly reduced the P95 end-to-end latency by 43% and increased throughput by 2.14 times. Most importantly, we verify that InferLog achieves faster inference performance without sacrificing log parsing accuracy. We then test adaptability. InferLog performs consistently well on the dynamic workloads with different QPS and across different LLM families, such as Llama and Mixture. Next, we integrate InferLog with existing LLM-based log parsers like Devlog, Lilac, and Logbatcher. With InferLog, this log parser shows a good performance speed-up, proving that InferLog is fully compatible and highly effective with existing log parsers. Finally, our ablation study confirms the contributions of each design module, removing neither the prefix-aware ICL refinement pair or the configuration tuning module noticeably degrades the performance. Our pair module pushes the prefix catch hit rate to over 90%, significantly outperforming other prefix catching strategies. And our proposed attention-based MAM model, it demonstrates significantly lower prediction errors. And the last figure shows the configuration searching process. InferLog quickly identifies configuration with high-performing areas, so thereby greatly reducing the time cost for online tuning. In conclusion, we have developed an efficient LLM inference system for online log parsing, successfully handling massive requests while meeting service level objectives. The key idea is greatly improving the prefix catching hit rate for the ICL part while optimizing configuration rapidly. For future work, we acknowledge that the prefix catching imposes strict requirements on having exact same prefix tokens. We plan to explore KV catch reusing for harness engineering in agentic system, and we also aim to extend this framework to more software engineering tasks beyond log parsing. So that's all. Thank you for your listening. Here is the link for the repo and my personal homepage. Thank you.